Hi. In the last module, we talked about the general linear model, or the GLM approach to analyzing fMRI data. In this module and the next one, we'll talk about model refinement, so how we can get the most out of our GLM model. And so we're going to talk a little bit about model building. So recall that the general linear model can be written in the following format. We have y is equal to x beta plus epsilon, where epsilon is normally distributed with a mean 0 and a variance covariance matrix V. Now, y is the fMRI data from a single voxel, strung out from n different scans. X is the design matrix, which is user-defined. Beta are the model parameters, which are the weights of the columns of the design matrix. And epsilon is equal to noise. Now, V is the covariance matrix whose format will ultimately depend on the noise model. So for now, we can basically just assume that it's independent, IID, so it's an identity matrix times some constant. Now, how good is this model? Well, the quality of the model will ultimately depend on our choice of the design matrix and the variance covariance matrix. So we're going to put a lot of energy into making appropriate choices for X and V, because that's going to ensure that our model is going to fit the data well. Proper construction of the design matrix, that's going to be the focus of the next two modules, and that's really critical for effective use of the GLM. And this process is not always so easy, and it can be complicated by the following properties of the bold response. One, it includes low-frequency noise and artifacts that are related to head motion and heart rate and respiration. Two, the neural response shape may not be known exactly. And three, the hemodynamic response varies in shape across the brain and also across subjects. So the first thing that we need to model and include in our design matrix is always, the predicted bold response. So we want to predict the shape of the bold response to a given stimulus pattern and assume that that shape is known, but the amplitude is unknown. And then we try to estimate this amplitude and perform statistical tests to see whether or not the amplitude is significantly different from 0 or not. If it is significantly different from 0, we assume that that voxel is active. Now, the relationship between the stimuli and the bold response we've already talked about is typically modeled using this linear time invariant system, or LTI system. And in an LTI system, the impulse, the neuronal activity, is convolved with the impulse response function, which is this hemodynamic response function. So we've looked at this cartoon a couple of times where if we have a block design, say we finger tap for 20 seconds, rest for 20 seconds, finger tap, rest for 20 seconds, then that's our experimental stimulus function. And so within the LTI system, we would convolve that stimulus pattern with the hemodynamic response function and get a predicted response like this green curve down at the bottom left here. Now, similarly, if we did an event-related design where we had, maybe clapped our hands at intermittent time points, now we would have an experimental stimulus function that looks like the one to the right. We would convolve this with the HRF and we would get a green function, a predicted bold response like the green function at the bottom right. So depending on what our stimulus is, assuming that the stimulus corresponds to the neuronal activation and that we have a known hemodynamic response function, we can predict what the expected bold response should look like and include that as a column in our design matrix. Now, this can be extended to multiple conditions. So let's say that we have 4 different conditions that we seek to compare. Let's say that we have a thermal pain experiment where we apply heat at different temperatures. And so condition A is at low temperature, and B, C, and D are at increasingly higher temperatures. And let's say that they're applied at different time points, like we see here on the left. Now, we could take each of these onset times for each of these 4 conditions, convolve them with the HRF, and get 4 different predicted bold responses, 1 for each condition. Now, each of these are then included in the design matrix as a separate column. And so then we can estimate the amplitude for each column and compare them with each other. For example, we can test whether or not there's a difference between condition A and condition D or something like that. Now, this is a very convenient way of modeling the data, but it makes a number of assumptions. First, it assumes that the neuronal activity function is correct, so that our stimulus function corresponds to the neuronal activation. Second, it assumes that the hemodynamic response function is correct. And then third, it also assumes that linear time invariant system is appropriate to use. So let's take a look at the second of those assumptions about the HRF. So often a fixed canonical HRF is used to model the response to neuronal activation. And the one that's typically used in the field is a linear combination of two gamma functions. And this allows us to model both the rise that occurs and also the undershoot that occurs after, say, 10 to 20 seconds. And if this is correct, then it's optimal to assume this shape. However, if it's wrong, which it's bound to be in a lot of places in the brain, this will lead to bias and potential power loss. And indeed, it's unlikely that the same HRF is valid for all voxels. And the true response may be faster or slower in certain areas of the brain, and the true response may have a bigger or smaller undershoot as well. So here's kind of an illustration that kind of shows that the HRF shape can depend both on the vasculature and on the time course of neuronal activation. So generally it's considered that assuming a fixed HRF is usually not appropriate, and it can lead to some troubles. So what should one do about this? Well, oftentimes one uses a much more flexible way of modeling the HRF, and one uses something called temporal basis functions. So to allow for different types of HRFs in different brain regions, we typically use these temporal basis functions. And so what are these? Well, we basically use a linear combination of functions that can be used to account for delays and dispersions in the HRF, so basically differences in the HRF across different voxels. And then what we do is we convolve the stimulus function with each of these basis functions to give a set of regressors. And then ultimately the parameter estimates give the coefficients that determine the combination of basis functions that will best model the HRF for the specific trial type that we're interested in and the specific voxel that we're studying. Now let's illustrate this. In the context of the LTI system, the bold response is modeled as xt equal to s, which is the stimulus function, convolved with h, which is the HRF. So in that case, we were assuming that we had a fixed HRF, maybe the double gamma one that we previously talked about. Now when we use temporal basis functions, here we instead consider modeling the HRF as a linear combination of several temporal basis functions, which we're going to call Fi of t. And we're going to model it in such a way that h of t is now a sum of these different basis functions that are weighted by different beta functions. Now to illustrate this, let's take a look at this little cartoon. So here, the hemodynamic response function is weighted by, at first, a function that looks kind of like the canonical HRF, and then two functions which kind of allows it to shift and widen. So using the linear combination of these three different basis functions, we can usually model a wider class of shapes and allow for the HRF to widen and shift in onset a little bit. And so now the point is we would take each of these basis functions and convolve them with the stimulus function and get a predicted bold response corresponding to that basis function, include that as a column in the design matrix, and that will have three columns corresponding to the HRF, and we'd estimate beta 1, beta 2, and beta 3. And once we have those estimates, we can reconstruct the HRF by taking this linear combination that we see here. So using temporal basis functions, the bold response can now be rewritten in the following way. We replace h with the sum of beta I Fi, and so basically what we get here is we see that x is now the weighted sum of beta I times the convolution times each of the temporal basis functions. And so as I said before, in the GLM framework, the convolution of the stimulus function with each basis function will then make up a separate column of the design matrix. And each corresponding beta will describe the weight of that particular component, and that will allow us to recreate the HRF for that particular voxel. That sounds like a very useful thing. So what kind of basis functions do we typically use? Well, there's a wide variety of different basis functions in use, and they vary a lot in the degree they make a priori assumptions about the shape of the response. So in the most extreme cases, the shape of the HRF is fixed and only the amplitude is allowed to vary. That's the case where we use the canonical HRF, for example. On the other hand, we could use something like a finite impulse response or FIR basis set that contains one free parameter for every time point following stimulation for every cognitive event type. And in this, using this type of basis function, we could basically model any shape that we want. So here's an example of the canonical HRF and its derivatives. You'll remember this from my little cartoon earlier on. So basically, including the derivatives allow for a shift in delay and dispersion away from the canonical form. So by weighting these, beta 2 and beta 3, so to speak, and the two other basis functions, we can slightly change the canonical shape and get more flexible results. Here's an example of the finite impulse response. So this is 1 at one time point and 0 everywhere else, and that 1 is shifted as we go across. So we're going to have one time point for each TR, basically. And so now, when we estimate beta, we're going to have a beta for each time point, and so using this we can recreate basically any shape that we want. So this model estimates an HRF of arbitrary shape for each event type in each voxel of the brain. So let's take a look at a couple of different basis sets and see how they perform on an example here. So here is the single HRF model. So now we just assume this canonical shape, and that will give us one column of the design matrix, and that's what this image of predictors illustrates. And let's say that we fit it to the data. Now the data is this bold line in the plot to the right, and the fitted one using this canonical is this dashed line. As you can see, it doesn't fit the data very well, and we're going to tend to, because the actual data is shifted vis-a-vis the canonical, we're not going to get very good results. Now, if we use the HRF and its derivatives, now we're going to get three different columns of our design matrix, one for the canonical HRF, and one for the time derivative, and one for the dispersion derivative. Now, if we fit this to the data, we're going to have three betas, beta 1, beta 2, and beta 3. And if we take the linear combination of those, once we've estimated it, you see that we fit the data much better in this case. Now, we've been able to shift the estimate HRF over a little bit, and we're able to better capture what's going on. We don't capture the undershoot very well, but the rise and the decline we capture quite well using the HRF plus its derivatives. Here's the finite impulse response. So now we have a different function for each time point. And so basically each time point we're going to have a 1 at a certain time point and a 0 everywhere else. So we're going to have lots of different columns here. Here it looks like we have about 15 different columns, one for each 2 seconds between 0 and 30. Now to the right we see that this fit is extremely good. We're actually a little bit too good because we're fitting not only the signal, but we're also fitting the noise in this case. We might be overfitting things. So in reality, we might, if we were to use an FIR basis set, we might want to put some sort of penalty that makes it not model the noise as much. Finally, we often assume that the stimulus is the same every time it's repeated, but often a stimulus can be parametrically varied across repetitions, and it is thought that this may be reflected in the strength of the neuronal response. One example would be when you had to do something like a go, no-go task, and the reaction time, the amount of time it takes for you to press a button, might vary between different repetitions of the example. In these types of situations, the parametric modulation can be modeled by including an additional regressor in the design matrix that accounts for possible variation in neural responses between trials. So here we have an example. If you look at the figure to the right, let's suppose that we have a number of repetitions of a stimuli, but the stimuli, each time we repeat the stimuli, the bold response, the height of it, of the HRF, differs a little bit. Now, let's say that we go in and we see that maybe the reaction time differed across the different stimuli. And let's say we have some measure of this. And so that's what these stick functions here in the middle are now showing. So in the first time we had a relatively low response, then we had a high response, etc., etc., etc. Now one way of modeling this is now using two different model predictors. The first is just assuming that each of the trials had the same neuronal response, and the second one is looking at what is the difference in the psychological events between, say, the grand mean and the one we observed on that trial. In that case, that would be a second type of condition that we would now convolve with the HRF, and we would get the estimated difference due to psychological effects, which is this second curve. in the model predictors. And if we use this, now the fitted response quite accurately fits the data, idealized data above. And now we can test for differences between psychological events or between repetitions by looking at this second regressor and testing whether or not it's significantly different from zero. If it is significantly different from zero, then we can assume that there is a trial-to-trial variation in the psychological processes. Okay, so that's the end of this module. Here we talked a little bit about model refinement for the general linear model. So this is the first of two-part modules where we're talking about how to refine the design matrix. So here we talked about things like temporal basis functions and parametric modulations. In the next module we'll talk about including nuisance regressors such as motion and drift and whatnot. Okay, I'll see you then. Bye.